Earth is in danger, facing an extinction event unlike anything seen before, more devastating than the asteroid that wiped out the dinosaurs, more deadly than the volcanic eruptions that killed off 96% of marine species and 70% of land creatures 252 million years ago. Instead, this great demise of life on Earth will be orchestrated by something we need, something we rely on, in fact. What will be the culprit? None other than our own life-giving sun. As our star gets brighter over the next billion years, the finely tuned balance that has kept our planet thriving for eons will begin to shatter. Our oceans, atmosphere, and tectonics will shift so drastically that Earth becomes completely unrecognizable. The question is, will anything survive? I'm McColgan and you're watching Astrum. Join me today as we uncover how Earth will change over the next billion years and witness what could be life on Earth's final fight. This is the story of the future of our planet. And although I mentioned it's our sun that has the potential to wipe out life, there's a lot of other stuff going on too. I'll take you through it all. But before we get started, a few disclaimers. Firstly, we'll be assuming that there is no human influence in any of this. We are covering how we think natural processes will play out on our planet without humanity's intervention, though we'll come back to humans at the end. Secondly, it's useful to point out that Earth's future is not very well defined. We can project a general idea of what might happen based on our knowledge of planetary science, geology, and biochemistry, but a billion years is a really, really long time. I mean, 1 billion years ago, there were no such things as plants, almost no oxygen in Earth's atmosphere, and the continents were clustered together into a single landmass. Our home was literally a different world. Earth a billion years in the future will be just as foreign. Nevertheless, all the predictions I'm about to share are based in science, even if they feel a little vague. So, without further ado, let's see what's in store for Earth. Run the tape forward. One of Earth's most unique features is its plate tectonics. And the first thing we notice is how fast plate tectonics shift, something my good friend James Stewart from Astrum Earth knows all about.
Yeah, thanks Alex. What we know is that Earth's plates have been moving for more than 3 billion years, and they're showing no signs of stopping. As per geologist Dr. Christopher Scotese's Pangaea Proxima theory, in 100 million years, based on the current trajectory of the continents, the map of the world looks something like this. Africa, which split into 2 continents a few million years earlier, collides with Europe and Arabia, closing the Mediterranean, Red Sea and Persian Gulf. A vast Mediterranean mountain range, possibly higher than Everest, will run from Spain to Asia. Australia joins Southeast Asia, compressing Indonesia and the Philippines into new mountains. North America and Eurasia move apart, widening the Atlantic Ocean. Southern and Baja California join Alaska, forming a new American mountain range, while the Rocky Mountains erode down into lowlands. In the hands of tectonics and subduction, the Earth's surface is incredibly malleable. Eventually, in 250 million years, the landmasses of the world converge into a new supercontinent, called Pangaea Proxima. The Atlantic and Indian Oceans close, bringing the Americas together with Eurasia and Africa. South America curls around the southern tip of Africa and Antarctica, creating an inland sea. The movement of these continents disrupts the global conveyor system of ocean currents. A lack of circulation causes water deeper than a few hundred meters to lose its oxygen, becoming unable to support most life, leading to another great extinction event. The land doesn't fare much better than the water either. Inland, the continent will experience semi-arid or desert climates, with extreme temperatures reaching up to 55 degrees Celsius. The only areas likely to be habitable for land mammals are those closest to the poles. But this configuration won't last forever. Eventually, Earth's land masses will fan out again, in an almost cyclical fashion. I've actually done a video about some of Earth's previous lost continents, so please click the link if you want to find out more. But for now, it's back to the future with Alex.
Whilst on the surface they look drastic, these shifting continents are nowhere near the biggest changes life on Earth faces. We all know that atmospheric carbon dioxide levels influence the planet's climate. Luckily, the Earth has a built-in feedback loop that naturally regulates these levels over millions of years. It's known as the carbonate-silicate cycle, and it works in 4 main steps. When a volcano erupts, it emits carbon dioxide into the atmosphere. There, it interacts with water vapor to form carbonic acid. This slightly acidic water condenses into rain and cascades onto the Earth's crust below. The carbonic acid in the rain reacts with the silicate materials in the rocks to form dissolved ions like calcium and bicarbonate, which get swept up by streams and rivers. Once in the ocean, these ions are used by marine organisms to build their shells and skeletons, which are made of calcium carbonate. You'll notice carbon dioxide reappears here as a byproduct. This process of chemical weathering has essentially pulled carbon dioxide out of the atmosphere and stored it in the ocean. When marine organisms die, their shells are eventually buried in the seafloor, forming carbonate rocks. Over millions of years, the oceanic crust, carrying these carbonate rocks, is subducted into the mantle, ready to be released via volcanic outgassing. And the cycle starts again. It's a delicate balance that keeps the planet's temperature, climate, and atmosphere in check when humans aren't getting in the way. But in 500 million years, something will have a much bigger impact on our climate than us or this cycle: the sun. Small, subtle changes our star has been going through all this time finally become apparent, and its effects are felt on Earth like never before. As a main sequence star, our sun is constantly fusing hydrogen into helium in its core. Since helium is heavier than hydrogen, over millions of years the sun's core is becoming denser and more contracted. Because of this, the outer layers of the sun move closer to the center too, and in the process, gravitational potential energy is released as heat and light. This increases the pressure and temperature of the core, which in turn accelerates the rate of fusion. The result is that the sun increases its energy output and in turn its brightness as it ages. This has consequences. As the sun gets hotter and brighter, it's also getting wider because of the extra energy being produced in the core. The sun is stuck in the middle of a game of tug-of-war between 2 forces, this outward pushing force generated by nuclear fusion and the inward pull of the star's own gravity. On the whole, this system looks stable, but zoom out to a timescale of billions of years and you can see that it isn't. As more and more hydrogen is used up, the sun's core slowly starts collapsing, while the outer layers grow larger. Right now, the sun is getting over 1% brighter every 100 million years. So, in 500 million years, the sun will be about 5% brighter than today. This extra energy warms Earth, speeds up reaction rates, and causes oceans to evaporate, which we'll come back to. This increase in reaction rates accelerates chemical weathering, pulling carbon dioxide out of the atmosphere faster than volcanic outgassing can replace it. Atmospheric carbon dioxide plummets. This is the start of the plant apocalypse. It seems the sun is not very good at gift giving. A planet-ending amount of heat and light is not exactly what we all wanted for Christmas. If you're looking to be a much better gift giver than the sun, then rather than get something fiery and destructive, why not pick something sleek, high-end, and innovative? Today's video is sponsored by Novium, the makers of the HoverPen Interstellar and HoverPen Future. These refillable, comfortable pens defy gravity thanks to the help of a magnetized base, allowing them to float elegantly on your desk. They're ideal for space enthusiasts, as they incorporate space into their design. The Hoverpen Interstellar stands at a 23.5-degree angle in a nod to Earth's tilt, and the premium version comes with a real piece of meteorite embedded in its tip. You can choose from an array of 4 colors, so there's something for everyone. If you're looking for the perfect gift this Christmas, why not scan my QR code or follow the link in the description below. Shipping is free to most countries, and for the next 48 hours, anyone who uses my link or the code Astrum at checkout can have 15% off their purchase. But how does the sun reducing carbon dioxide in the atmosphere cause plants to start dying out? Think of plants like tiny factories. Using photosynthesis, they turn carbon dioxide into sugar, which they use to grow and build new things. But they also need to burn some of that sugar for energy to keep everything running smoothly, a process known as respiration. When the amount of carbon dioxide gained from photosynthesis is equal to the carbon dioxide lost from respiration, the plant is at its compensation point. It is breaking even energetically. To grow big and healthy, the plant must make more sugar than it burns. If it doesn't, the plant eventually dies. Photosynthesis comes in 2 main forms, C3 and C4. Most plants, including trees, grasses, root vegetables, cotton, and staple grains like wheat, rice, and oats are C3 plants. They need relatively high levels of carbon dioxide because their system isn't very efficient. According to a 2019 study from the International Journal of Astrobiology, within about 500 million years, the concentration of carbon dioxide will fall below 150 parts per million, lower than the critical threshold needed to sustain C3 photosynthesis. But this extinction event is a slow burn. Plant groups die off one by one, well before the 150 parts per million level is reached. However, it won't kill them all. There's still the C4 plants, which make up just 5% of Earth's plant biomass today. They can survive on much less atmospheric carbon dioxide, just 10 parts per million, because they have evolved a different enzyme system and therefore have a higher carbon dioxide resistance. It's thought C4 plants could survive anywhere from 800 million to 1.2 billion years into the future. But even with this brilliant ruse up their sleeves, they can't outlive the brightening sun. In 1 billion years, the sun is just over halfway through its main sequence lifetime. As its core gets even denser, the rate of fusion increases too. Today, the sun turns 600 million tons of hydrogen into helium every second, in the process converting about 4 million tons of matter into energy. The more energy it releases, the more luminous the star appears. And if we travel forward in time another billion years, the sun becomes 10% brighter than it is today. The effects on Earth are disastrous. Models vary wildly, but some believe the surface temperature could skyrocket to a sweltering 50 degrees Celsius or more than triple the 20th century average. This transforms the planet into a near uninhabitable world. Oceans evaporate faster than rainfall can replace them. Vast regions turn into deserts reaching over 70 degrees Celsius in the daytime. Without photosynthesis, oxygen levels in the atmosphere fall to about 1% of what they are today. This would be devastating for complex life that relies on it to breathe. But it's more likely they'd starve to death before this became an issue for them. With no plants to eat, herbivores die out, and carnivores quickly follow. So far, we've covered how rising temperatures affect the carbonate-silicate cycle, cause atmospheric CO2 levels to drop, and spell the end of complex plant and animal life on Earth. But there's one more key piece to the puzzle: oceans. A billion years from now, 27% of our modern oceans have already been subducted into the Earth's mantle. The rest won't stay put for long. As the sun grows hotter, the oceans start to evaporate, turning the sky into a thick, steamy greenhouse. Water vapor fills the lower atmosphere, warming the planet steadily. The water cycle persists, rain still falls and rivers still flow. Things remain pretty stable for a while. As that water vapor accumulates in the atmosphere, it creates an insulating blanket around the planet. Temperatures continue to rise, eventually triggering a runaway greenhouse effect, increasing the Earth's temperature uncontrollably. The only other planet where we've seen anything like this is Venus. Today, it's completely uninhabitable at around 460 degrees Celsius, with pressures similar to being 900 meters under the ocean. When we gaze over at the goddess of love, are we seeing our own future? Depending on the pace of this evaporation, Earth is doomed to lose its oceans within 1 to 1.5 billion years. Yet Earth won't be entirely dry, at least not right away. Deep down, below the crust, huge amounts of water, perhaps several times the amount in Earth's modern-day oceans, are still locked away. Over time, some of that water seeps back to the surface through geological activity, but it won't be enough to bring back the seas. The last place surface water persists are the poles, but with no rivers to feed them and no life to decompose, these polar lakes are no more than sterile, nutrient-poor puddles. Eventually, even these evaporate too. Earth transforms into a barren, desert world. Massive dune fields stretch across the equator, and salt flats mark the old ocean floors, similar to the Atacama Desert in Chile. Without surface water, the Earth's crust dries out. Without lubrication, subduction can no longer take place. Tectonic activity grinds to a halt, freezing Earth's plates in place. In the absence of that geological action, our planet slowly begins accumulating impact craters and shield volcanoes over mantle hotspots. Over millions of years, these volcanoes release trapped carbon dioxide from the mantle into the atmosphere. The planet gets even hotter, a dry, suffocating world wrapped in a thick blanket of carbon dioxide and water vapor. The only remaining hideouts are tucked away in underground ice caves or in high elevation mountains, where the final smatterings of water could remain. Here, protected from the searing surface, we find Earth's last living creatures, salt-loving microbes capable of enduring brutal heat and dehydration. Some might even drift high into the atmosphere, surviving in cooler layers above the scorched ground, much like what scientists speculate could be possible on Venus, which potentially has a habitable zone 51 to 62 kilometers above its surface. 150 million kilometers away, the sun continues to brighten and intensify. 2.8 billion years from now, it is 28% brighter than today, pushing surface temperatures to around 190 degrees Celsius, even at the poles on Earth. They put up a good fight, but then the last of the microbes perish, and with them, all signs of life disappear. If a team of advanced alien scientists flew past Earth 3 billion years from now, they wouldn't detect a single biosignature. They'd have no idea that our world once teemed with the buzz of lush rainforests, rushing rivers and waterfalls, and a chattering human civilization. They'd see a barren world, a stagnant rock, waiting for the inevitable. In roughly 6 billion years, we approach the end of not just the Earth, but our entire solar system, as our sun begins dying too. As it uses up the last of its hydrogen stores, fusion in the core stops. That outward pressure generated by the reaction disappears, so there's nothing to counter the core's gravity, and it starts collapsing. As the sun's core contracts and heats, hydrogen fusion ignites in a shell around it, driving rapid expansion and a surge in brightness. Within another billion years, the sun's luminosity exceeds 1,000 times what it is today, as it swells from a subgiant into a red giant. Red giants cool and shed vast amounts of mass through dense stellar winds, material that could one day seed new stars and planets. As the sun loses about half its mass, its weakened gravity lets the outer planets drift outward, roughly doubling their orbits. Earth's orbit expands to about 1.5 astronomical units, but tidal forces eventually pull it inward again. At the red giant's peak, in about 7.6 billion years, the sun's radius reaches 1.19 astronomical units, 256 times what it is now, and engulfs the Earth, consuming our planet entirely. Until recently, scientists differed on how likely it was that Earth would be swallowed up by the sun, with some suggesting our orbit could expand as the sun grows, moving us out of the danger zone and saving us from this grisly fate. But a new study using data from NASA's Transiting Exoplanet Survey satellite shows planets are being destroyed all over the galaxy, and it doesn't look good for Earth. They found more than 130 potential planets, but there were very few around red giants, implying they had vanished. It seems stars swallow their inner planets far more often than we had previously thought. Lead author, Dr. Edward Bryant, stated that we expected to see this effect, but we were still surprised by just how efficient these stars seem to be at engulfing their close planets. So, with Earth and the other inner rocky worlds of our solar system gone, the sun sheds its outer layers, leaving behind its hot, dense core. Over trillions of years, this white dwarf will gradually cool and fade, taking with it any memory of the solar system it once ruled. Even though this is written in the stars, it doesn't mean it will spell the end for us. I mentioned at the beginning that this is what would happen assuming no human intervention, but humans have a compulsive habit of rewriting nature's story. We've done it so many times already. Just imagine what we may be capable of in a few million years, if we make it that far. We could intervene to find ways of adapting to or even preventing some of these events from occurring by terraforming parts of Earth for survival, or perhaps even colonizing other planets. The Earth story may end, but ours doesn't have to. And even if it does, that's okay. After all, we are made of stardust, so it's only fitting that we're reunited with the stars. Patreon members got access to this video ad-free, and more importantly, they keep Astrum grounded in a community passionate about space, not just YouTube AdSense and algorithms. So sign up with the link in the description. Being a member means you're part of the reason Astrum can focus on the kinds of videos people actually want to watch. It's where our most engaged viewers are, people who care about learning, exploring, and seeing what's out there. If that sounds like you, join the Astrum Patreon today and be part of where we're headed.